Okay, so number 5 is really a couple things. It's do you understand what rotational inertia is? That helps. But also it's simply about angular momentum, conservation of angular momentum. So when you see this satellite is a spinning cylinder and then it unfolds these solar panels, hopefully the first thing that comes to your mind is the figure skater or our rotating stool in the classroom, that when you put your arms out, you distribute mass further away from your axis of rotation, give you a greater rotational inertia, um, making you go slower because angular momentum is conserved when there's no external torque. So a satellite spinning out in space, we would expect there would be no air resistance and nothing that would add or take away any angular momentum. So all it's saying then is that the angular momentum before, I can write it like this, before the solar panels are unfolded has to be the same as the angular momentum after they're unfolded. So they're using these A and B. So it says solar panel, the satellite then has a rotational I final. So we're comparing initial and final. I guess I put before and after, but so we can write it like this using the right terminology. We can say that the rotational inertia, I'm going to use the initial times the angular velocity initial has to be the same as the rotational inertia final times the angular velocity final. So we know that when he puts the solar panels down, that the rotational inertia has to go up, right? Because he's now extending mass outward, just like putting our arms out. So if the rotational inertia increases by spreading out those solar panels, then by the law of conservation of angular momentum, that satellite's angular velocity must go down. So this problem's trying to be fancy comparing A and B, but it's basically saying, if we look up here, A is some coefficient that describes how the final angular or rotational inertia is compared to the initial. So when the solar panels go down, we know that the final angular velocity has to be smaller. So that means A should be less than 1 because the final velocity or final inertia has to be, I'm sorry, we're talking about rotational inertia. The final rotational inertia has to be greater. So A has to be greater than 1 because A has to be a value bigger than 1 to make the final greater. So that gives us two choices. And then we also know by conservation of momentum that if the rotational inertia increases, then the angular velocity must go down. So here, if the final angular velocity equals something times the initial angular velocity, we know the angular velocity has to decrease. So that means B must be a value less than 1. So A has to be greater than 1. B has to be less than 1. Two things to know here. One, mass goes further from the axis of rotation, more rotational inertia. Two, more rotational inertia means less angular velocity because the total angular momentum has to be the same before and after they extend those panels. We did this one in class, but this was essentially understanding the concept that change in angular momentum is always going to be equal to 0 when net external torque is equal to 0. So again, it's about the system. So the system is defined here as assume that which is defined describes an action by the child, the result of the child platform system. So the child is part of the platform. That means anything the child does force-wise or torque-wise is not a net external torque. So when the child moves towards the center of the platform, for example, he is decreasing the rotational inertia, so the whole system then has less rotational inertia, so that we would expect the platform to rotate faster so that momentum is conserved. Still, no net change in the total momentum. Child moves away, we would expect the opposite. The mass is now distributed further from the axis. I goes up, so omega has to go down, but I times omega stays constant. C, the child moves along a circle opposite the direction of the rotation, so that means the platform's rotating in the counterclockwise direction. So he's walking in the clockwise direction. So we can expect total angular momentum to still stay conserved. If you think about what happens as he walks on it in one direction, we would expect he now has angular momentum in the clockwise direction. So that means the platform must speed up in the counterclockwise direction. And that's a Newton's third law thing too, because as he pushes forward or pushes backwards to move forward, he is causing the platform to speed up. So none of these actions, because number one, they're all internal forces causing internal torques, so the total angular momentum would not change of this system. We did this one in class as well. This is, you did the balancing act. I expect this, I think we were almost 100%, so we won't really spend a lot of time here, except to know that if we want to put a block somewhere on this so that it doesn't rotate, then that means the sum of the torques have to equal 0. So that means all the torques causing a clockwise rotation, right, which would be this one, has to be the same as the total torque creating counterclockwise direction, which would be this one. And then we know that the pivot here is exerting a force on the platform, but since it's at the axis of rotation, there'd be no torque because we're talking about force perpendicular to the distance to the axis of rotation in the clockwise direction has to be equal to the same thing in the counterclockwise. So in order to do that, we would have to know, number one, the mass of each block, and then number two, right, that would be, so these forces would be mg because they're just blocks on there. And then number two, if I'm looking for, this is the second block over here, so this is what I'm trying to find. So I need to know that, I need to know that, and I need to know that. That's just a net, zero net force, zero net torque if we want something to not do anything, rotate or move. And then our last question here is an easy one, but a lot of you missed this one for some, I guess, some varied reasons. If you read it all the way through, I guess one thing you have to see at the end is that it says there is considerable friction. So we'll get to that at the end. However, excuse me, we know that net force produces an acceleration, so that means net torque produces angular acceleration. We know that acceleration is change in linear velocity over time, so angular acceleration is simply change in angular velocity over time. So you look over here on the y-axis. The y-axis is literally omega over t. So the y-axis is just angular acceleration. So this is a Newton's second law problem. We actually did this lab. You measured the acceleration of a fan cart and you varied the force of the fan on the cart, and we measured it, we graphed it to see that acceleration is directly proportional to net force. So angular acceleration, remember the y-axis here, is directly proportional to net torque, right? That's what this equation is saying. Forces make things accelerate in the linear direction, meters per second squared. Torque causes things to rotate, radians per second squared. So we know that if I increase the torque, then I'm going to increase the angular acceleration in a direct relationship, which means we have A, C, and B all showing that. This doesn't make any sense. If I increase the torque, I don't get less acceleration. Now the considerable friction part. At zero net torque, I wouldn't expect there to be any acceleration from 0, 0 because there's considerable friction. Friction would be, in this case, a counterclockwise negative torque. So this doesn't make sense. So what makes sense is that there has to be some minimum amount of torque before the thing even starts to have an angular acceleration. So A, the fact that there is a negative y-intercept shows me that there's friction, right? That's that negative y-intercept. If I look at B, that would be another net external some torque that would cause it to be having an angular acceleration positive y-intercept with zero applied torque. So that would be kind of the opposite of friction if there was something causing it to rotate, before someone's pulling on it or another mass hanging from it. But the answer here clearly has to be A. This is just a second law problem applied to rotation.